Welcome to the webinar, Impact of Human Factors on Operator Response to Alarm, Lessons from Process Industry Incidents. So as we go along, if you have questions about the presentation or related material, I would suggest entering them into the questions box because we probably won't have a lot of time at the end to go through them. But we will get back to you with answers to those questions. My name is Todd Stauffer. I'm the Director of Alarm Management here at exida. Alarm management includes human factors, certainly related to the operator's response to alarms, and I'm involved in the creation of the standards for alarm management, mainly ISA 18.2. Been involved as an editor and voting member since 2005. And then also with some of the subsequent work to create technical reports and to create a new standard on safety controls, alarms, and interlocks. I want to give a shout out to my colleague, Peter Culbert from the exida Ireland office, who helped me put this presentation together. And if this is your first webinar, welcome, thank you for joining. A little bit of information about exida. We were founded over 20 years ago by two gentlemen who wanted to make the world a safer place, particularly process plants. And that started initially with a focus on functional safety. It expanded to include other major areas of risk in a plant, including cybersecurity and alarm management. We are an industry leader in the certification of people and products for functional safety, cybersecurity, and other things. So if you've ever put together a safety instrumented system and worked with SIL-rated equipment, chances are exida did that assessment, that SIL assessment. We also have a suite of software for safety instrumented system design called Excellentia, and it basically helps you go through the whole entire functional safety life cycle from beginning to end. It includes, as one of its modules, a tool called SIL Alarm, which is an alarm rationalization tool. So let's talk about today's webinar. We are going to talk about human factors, trying to get a handle on what we need to know to understand how operators make decisions and process information with the goal of being able to design better systems, in particular the human-machine interface and the alarm system. So we're going to look at some of the key cognitive processing factors that relate to that or influence that. We will also look at how operators respond to alarms. When you analyze incidents, what kind of information should you collect? And then we're going to take a look at a bunch of incidents from industry and try and learn what happened and what we could do differently going forward and potentially apply those lessons to the current plants that we work with. So let's start with an introduction and some motivation on this webinar. There have been many articles and books that I've read that when they talk about human error and process incidents, there are many studies that show the same number, basically 80% is the magic number of the percentage of incidents that are attributed to human error. Now, from the occupational safety side, the sheer number of incidents has actually gone down over the last 20, 30, 40 years. But in the process safety world, that's not true. We've not really had a reduction in the number, and we've not had a reduction in the severity of the incidents either. And in fact, what we are seeing now is a repeat of some of the major problems and issues that we've seen in the past. So history is definitely repeating itself and costing more as it happens. So for this presentation, the purpose If you are looking to identify things that people did wrong so that you can assign blame, this is the wrong presentation for you. Instead, what we're going to do is try to understand better the mechanisms and factors that shape operators' behavior, how they think about things, how they come to conclusions, how they take actions, and how they make decisions. So that's the purpose of this presentation, to again take those lessons and design a better system that supports the operator better. So let's start with some human factors basics. First, how do people process information? It starts with our senses: sight, sound, touch, smell, taste, etc. is the genesis of an input, and we go through a perception process to understand what those stimuli mean. In some cases, we can go right from the perception of that sense, what we see, to a response, and an automatic corrective action gets performed, subconsciously responding to something. An example of that would be if we were driving a car and we noticed we were starting to veer off the road, we wouldn't need to spend time thinking about what's happening or how we should correct it. You would automatically change the steering wheel. You would turn the car to be able to automatically not veer off the road. So not a lot of thought goes into that. So that's one pattern of response. We're going to talk about 3 different patterns of response based on operator experience level. So you could think of the going directly from a sensory input to a response as a skill-based response. The operator knows the situation so well that they don't even need to think about it. The second type of a response takes a little bit more cognitive processing. We take in the perception, and now we have to compare it to what's in our memory banks to look for similarities or recognition, or how does this pertain to the rules that we know or follow. Based on that, that will give us the input probably for what action we should take. And then the third response is one where we truly do need to do some significant thought about what the input means and the appropriate corrective action to take. So we are accessing long-term memory, we're working with our short-term memory, our working memory, and that takes a lot of cognitive processing power in your brain. There's a limited amount for that. So that's why, for the most part, we want to try and make decisions or take actions without needing to put significant thought into it. And that's typically what happens with someone who's an expert at a certain process. And that expert responds in what we call a skill-based behavior, where they're very, very familiar with the task, and essentially based on that input, sensory input, they're able to take that to kind of an immediate response, a subconscious or automatic response, along the lines of what's called level 1 thinking, if you're familiar with Daniel Kahneman's book. The second behavior is a rule-based behavior. That's where we look at the inputs, the sensory inputs, and compare that to rules that we know. So if this happens, then we should do that. So we are comparing to rules, and then based on those rules, we are executing the action. The last category is called knowledge-based response or behavior. In this case, we don't have significant experience with a certain task, and we do need to put a lot of thought into understanding what's happening to make the right action, or to come up with what the right response or appropriate response is. So we're doing a lot of thinking about it, perhaps examining what we think we should do against some rule sets that we have, and then using that to make the corrective action. Now, most of the time, an expert operator is going to be doing a lot of tasks and a lot of responses in this skill-based area. But sometimes, depending upon the task, they will go back and forth to these other areas as well. Now, there are different types of errors that can be made depending upon which of these three kind of behavioral regimes you are in. And here's an example of what that error taxonomy looks like. For somebody who is an expert operator and responds in a skill-based approach where they really understand what's going on and know what to do, what kind of errors do they make? Well, they know what to do. They know the right thing to do. So when an error gets made, it's not because they didn't know what to do. It's because some other element failed. Maybe they made a slip, like entered the wrong set point when they intended to enter a 5.0. Instead, they entered a 50 and didn't realize it. Or they had a memory lapse where they're executing a startup procedure that they've done 1,000 times, and because they're multitasking, they forgot to do the last step to close a valve. Those are the kind of errors that an expert makes when they're involved with a skill-based response. Now, if we look at non-expert operators, they make mistakes, knowledge type mistakes. So if they're executing a rule-based behavior, their mistake could be they chose the wrong rule as to how they should respond, or they have the right rule, but they just applied it incorrectly. Knowledge-based then is when they really don't know how to respond appropriately. They don't have experience, they don't have knowledge, and that would certainly be an area that you would want to consider addressing via training, which we'll talk more about in a second. And the last type of human error is called a violation. This is basically where the operator, the human, does not perform the action as expected or documented. Violation sounds like a very negative thing. It can be indicative of normalization of deviance, which is essentially acceptance of doing it in a different way that you're supposed to, or it could actually have a positive intention aligning with the law of least effort, which basically says humans are always trying to figure out how to do something easier, quicker, faster. So they will constantly be experimenting to try and do stuff that way. So that might mean that they cut out a couple of steps in a startup procedure, all in an effort to make things go quicker and better, not for personal gain typically. So that's an example of what violation could be. It could also be an example of where the operator is not willing to take the appropriate action because there's a cultural element that tells them that they actually shouldn't. For example, if the necessary action is to shut down and they don't shut down, it could be because there is an operations culture that says production is more important than safety and you shouldn't shut down. Even though we're going to pay lip service to safety, the reality is that's not what's most important. So you might see a difference between what's expected versus what happens in that situation. And now let's look at where those errors show up in the response and assessment pattern. So the mistakes occur at the front end of the process where we're taking in the sensory inputs and trying to make sense of them, or we're trying to plan, figure out what is the course of action that we should take. These kind of errors, the ones that non-expert operators make, would benefit from additional training to correct those situations. If we look at the types of errors that the expert operator is more prone to, that can occur with a slip where they open the wrong valve or close the wrong valve. They had the correct intention, but they just ended up executing it incorrectly, or they forgot to do something because they had a memory lapse. For those kind of errors, additional training is not helpful and can actually be considered detrimental and punitive. So you do have to kind of understand and gauge that when it comes to figuring out what the appropriate remediation is. So training, if the errors are up here, for experts, training is not necessarily going to help. What you would be better doing is to make some changes to the HMI interface, for example, to prevent typical slips from occurring, and to maybe create some job aids that help the operator to not be likely to have memory lapses. It's kind of the principle behind why airline pilots have a checklist that they go through when they do their walk around before taking off. They've done it hundreds of times before. They know very well what's on that checklist, but they've gotten so familiar with it that stuff can happen. So the way that they prevent those kind of memory lapses from occurring is by making them go through a checklist. Other ways that operators can make errors when responding relate to cognitive biases, particularly for your experienced operators that are responding by a skill-based behavior. So the quick subconscious automatic response. One bias that impacts operator response is called recency bias. That means events that have occurred in the more recent past will be given more credence as more important when assessing the right course of action. Confirmation bias is another bias, and this is a really important one. It means that somebody has already determined what they think is wrong and the appropriate course of action, and then they either choose not to seek additional input, or as other input and cues come in, they choose to ignore anything that disagrees with their current theory. So they essentially confirm what their theory was because they ignore anything that goes against it. Overconfidence. If you've ever heard the saying that 3/4 of drivers think they are, or 75% of drivers believe they are above average skill as a driver, something that's statistically impossible. And then the last one we're going to talk about is hindsight bias, which is the tendency to take a look at events that have occurred in the past and think that they are more predictable than they really are, thinking that, oh, we would have never made that mistake, or our operators would have never done that. If you take that attitude, then you're going to miss the opportunity for some of these lessons learned, and you may not respond appropriately if you're in the operator's shoes. So other things that we need to understand from a human factors point of view: situation awareness. This is the concept of the operator taking in the cues and using their mental model, their understanding of how the process works, to figure out what those cues mean. What do they mean immediately? What do they mean in the near future? And what does it mean as they project things out in the further future? So where is the process heading? What is happening? It's their ability to truly have a good handle on what's going on with the process. And strong situation awareness relates to having a rigorous mental model, which is the operator's understanding of how the system operates and how the process behaves. Things like if you have a pressure vessel and the temperature is going up, you would probably expect the pressure to go up as well. That's an example of the operator's mental model. So it guides them on what to look for and what to expect. It gives them default information even to fill in when data is missing or not available. They have an expectation of what is happening. And the more experienced the operator is, the better the mental model that they typically have, with the more information and the more data that they have in it. Now, when they go to respond to something or figure out what's going on, one of the things that they're doing is using their mental model to do kind of simulations, mental simulations of what is going to happen if I do this or this, so that they can figure out the appropriate corrective action to take. Now, there are a couple things that get in the way of situation awareness that we're going to look for as we analyze our incidents. The first one is an errant mental model. That means your model of how you think the process works and how the equipment interacts is incorrect for some reason or another. The second point is attention tunneling. This is when the operator focuses too strongly on one theory of a problem or one area of the process, given the alarms that have occurred, and are ignoring other relevant information or other relevant alarms that would indicate that they should perhaps consider other areas or other theories as well. So we're going to see how those show up. And then the last thing that we want to talk about is, how do operators make decisions in critical situations? They do not actually make it in a very rational and logical way that you might think of initially, where one would come up with what all the possible alternatives are, create in your mind the criteria for how you'll evaluate them, and then give each one a rank and come up with the one that has the best score. That is not the way people effectively make decisions under stress or in critical situations. And a lot of this information comes from studies of firefighters who have very critical and stressful situations that they are making decisions for. And what they found is expert firefighters use their intuition and gut feelings to kind of match patterns of what they are seeing in the current situation versus what they have seen in the past. And they look for essentially the first workable option to execute for response. So they are not trying to come up with every possible permutation for a systematic evaluation and trade-off. They're trying to match the cues that they see to the patterns that they've observed in the past, and then go with what they match and assume that's the right approach. And then they'll update that as they go, as new information comes in, and they're using their mental models to simulate what's happening. So this is the way experts effectively make decisions in critical, stressful times. It works well for expert operators, called recognition prime decision models, but it doesn't work so well for novice operators because they don't have a rich enough understanding of what's happened in the past and mental models, such that the first workable option that they come up with might actually not be a very good one. So now let's move on to operator response to an alarm. There are 3 steps that we like to think of in the operator responding to an alarm. The first step is detecting that the alarm is present. And if you have a HMI with lots of flashy colors and flashy graphics or lots of nuisance alarms, it may be hard to detect the presence of a new alarm. Once the alarm is detected, then the operator needs to diagnose what the problem is, determine what the appropriate corrective action should be, and then take that corrective action to respond. So when we analyze incidents, what do we see? We say the end result of the action that the operator took, and we compare that to the action that they should have taken in hindsight. And when it's not what they should have done, sometimes or very often that gets labeled as operator error. But that's not really fair, because if there are problems in these first two steps with inability to detect the alarm or to see everything that's going on, or the operator is led down the path to diagnose the problem incorrectly based on nuisance alarms or based on the way the HMI portrays the information, then of course they're going to make an incorrect action. So just seeing an incorrect action at the end of the chain doesn't mean, and is not sufficient to mean that it's operator error. We need to look further and really understand what has caused it or what created it. So when we think about what the operator does in response to an alarm, typically they acknowledge it and then start to think about what they have just done in terms of operations and whether that might have been the cause of the situation. They compare to scenarios in the past when they've seen the same thing and think about what they did then to correct the problem. And that helps them formulate what the appropriate response is to take, and then they take that response. So what are the typical problems that operators encounter? Alarm floods will impact their ability to really get a good handle on what's happening, to figure out which alarms are the most significant ones and respond in a timely fashion. They may not be able to do that before an incident occurs. Alarm masking and psychophysics basically means that the salience of the alarm is not sufficient for the operator to either detect it audibly or visually. So there's too much noise for them to really notice or for that alarm to really stick out. Another common problem is nuisance alarms, alarms where the operator doesn't actually really need to take a corrective action, or when they do take the action, the situation doesn't clear. What nuisance alarms lead to, if they're not addressed, is operators ignoring alarms. So they normalize the alarm in the process state by accepting the fact that here's an alarm and it doesn't require me to do anything. So that's a normalization of deviance that we want to really stop or design out or prevent that from occurring. There's also problems with design of the text messages that are displayed to the operator so that they don't really understand what's going on, and the prioritization incorrectly identifying the importance of one alarm versus another, that can lead to issues and incidents as well. So now let's move on and analyze some incidents. What's the framework for analyzing an operator response to an alarm error? Well, first, the way we're going to think about this is modeling incidents using what's called an event chain, which means there's a condition that occurs that causes an event that leads to another condition that causes another event, and so on until we ultimately end up with an incident. So the way we figure out what happened or come up with the root cause or the initiating event is typically to start at the incident and work backwards. Now, it's somewhat subjective how far back we go or what events we stop at to consider as the initiating event. In some cases, we'll stop at an event that's familiar to the organization and is acceptable as an explanation. In other cases, we'll stop when we get to an event that we know we can do something about. And then in other cases, we stop when we get to the point where there's a human involved, because we may not be able to go any further back because we can't get into the operator's mind to move through and understand what led them to make the decision that they did. So sometimes we stop right there because of the impracticality of backtracking through the human event. Now, if you are able to interview the operators and understand what they were thinking that is ideal and is very valuable and will help you go beyond or go further backwards than the human error point. And that's definitely what you want to do if you can, but you need to create a environment where the operator doesn't feel like they're being blamed, but that you are truly interested in getting at the root cause of what caused them to think the way they did or to make the decision that they did. So when it comes to an operator response to alarm incident, here is some of the information that you might want to collect to help you figure out what happened and get to the root causes. So you want to collect the history of alarm activations and operator actions right around the time of the incident. We want to look at any suppression actions. We want to look at set point changes to alarms, changes in alarm configuration, look at the rationalization information. And here's an interesting one, the training materials. What did the training say that the operator should do when these particular alarms occur? It's an interesting thing to look at to compare to what they did actually do to see whether they're following their training. And because sometimes training leads them down the path to take the wrong action. There are incidents like at 3 Mile Island where the operators actually did essentially follow what they had been trained to do, but it was the wrong thing to do for the situation. So looking at the training material is very relevant. We also want to understand the overall alarm system performance. How many alarms were the operators getting typically? Were they being subjected to alarm floods? Was that in any way, shape, or form part of their response? Once we have this, then we can dive into an analysis to try and get to the what happened. And for our purposes, there are 3 major categories of failure that we would look at. First is there was no alarm even generated for the operator. And that could occur from, damage to a transmitter or a fault where the alarm is not even generated. So there's not necessarily or typically a human factors element to that, but this is a frequent cause of incidents. Second one is the alarm occurred, but the operator did not take any action. And then the third one is the alarm occurred and the operator did not take the correct action. So we're going to analyze our incidents based on these major categories to help figure out what happened. And then you can see we can dive down further to try and get to the root cause, if you want to call it that. So let's say the operator misdiagnosed an alarm or misdiagnosed the situation. They dismissed an alarm, didn't respond to it because they didn't think the alarm was relevant, and that was an incorrect diagnosis. So that's an example of how we might use this incident Y tree to get to the bottom of it. And I want to give a shout out to my colleague Nick Sands, who actually created this. So now we are going to analyze some incidents and try and take away some lessons learned. So first, I want to caution you to beware of hindsight bias. So we don't want to look at things and think, we would have never made that mistake, or they should have known better, because we won't get the benefit of the lesson that we could learn. And we want to analyze the role of the human in the accident, not from the point of view of what they did wrong, because that's just blame, but we really want to know, why did it make sense for them to act the way they did? And what you'll find is 98% of the time, the action that the operator took was logical to them, given the information that they had. So although it may have turned out to be the wrong thing, they didn't take the wrong action on purpose or maliciously. They actually thought it was the right thing to do. So we want to understand, why was that? Because we might need to change some things, or we should be able to change some things so that that doesn't happen in the future. So let's look at our first example, a refinery in Canada during the winter, where we have a level control valve that gets frozen closed, basically cutting off our incoming flow. Well, as part of the failure, it actually generated a high level alarm, which when the operator got it, decided that the appropriate corrective action was to reduce the set point. So that was a spurious alarm. A couple minutes later, they got a second alarm. It was actually a low alarm coming from a redundant transmitter over here, indicating that the level was really low, not high. Unfortunately, the operator thought it was a second high alarm, essentially a high alarm. So the action they took was to reduce the set point even further. Now, they did not take any action for 8 hours. The level in the tank continued to go down until they realized from the pump starting to cavitate that they had a problem. And unfortunately, they were not able to restore level before they lost the water flow and the steam feed to the plant in the middle of January. Not a good thing for a refinery in Canada. So let's analyze what happened. So using our incident Y tree, why did the operator take the wrong action? Well, they thought they were experiencing a high level situation. Now, was that a legitimate response from them, or was that an error? Well, it's hard to tell. Perhaps at the high alarm occurring, it's understandable to think that the operator might have responded incorrectly. But when the second alarm occurred, you would think that you would do a little bit more elaborate investigation of what was happening and to cross-check to the other information that you have to validate the situation. And in this case, they had a redundant level transmitter that they could have used to check what they thought was happening. So this was either an error on the operator's part, or maybe this was not part of their training to say, hey, this is what you should do. You should always be looking at the other information that's provided to you to confirm your mental model, to confirm your assessment of the situation. Now, they did also have issues with situation awareness when these alarms occurred. One of the shortcomings was the way the HMI was designed, the process graphics. The symbol for the level controller changed color to indicate there was an alarm, but it didn't change color for the level transmitter, which meant when that low alarm occurred, there was no visual indication on the process graphic that it was coming from a different location. So this might partly explain why the operator didn't pick up on that. They also had trouble processing the new alarm because it was one of 15 standing or stale alarms on their alarm summary display. And if you looked at the alarm summary display, looked at the information that was shown, a series of columns, the information would have been identical for a high versus a low alarm, all except for one column in the display of 2 letters. That would be the only difference between a high or a low. So the operator would really need to be concentrating and looking for that to be able to pick up on the fact that it wasn't the alarm that they expected. And then another potential contributing factor, and you probably won't hear this one very often, was operator workload. They may not have actually had enough to do to keep them engaged. The fact that they didn't interact or make changes with the controls for 8 hours makes you think that potentially they didn't really have a strong interaction with the process. So what did the company decide to do when they did their investigation? Well, they decided that the way it should be resolved is to add a low alarm for both the level controller and the level transmitter. So you got to step back and think, would that have prevented the situation from occurring? No. Does that address the underlying problem that we've identified? No, it doesn't. In fact, it potentially makes the situation worse because now we have even more alarms that could be generated and give the operator more information to have to go through and figure out what's going on. So here's an example of an incorrect action coming out of an incident investigation. Next one we'll look at is a scenario where we had some pump leaks at a chemical plant where they were transferring reagent to a neutralization area, and the reagent pumps developed some significant leaks that were collected in a sump. There were some level measurements on the sump and alarms, and the operator got both a high and a high level alarm for the sump, but they ignored them because they focused their attention on the neutralization area and the alarms that were being generated there because it was being starved for reagent. So the operator tried to correct the situation by focusing their attention and their actions in the neutralization area. Needless to say, they were not able to turn the situation around. And it wasn't until the next operator came in on second shift that they realized what had happened. The next operator did their rounds and realized that they had actually spilled 10,000 gallons of chemicals into the environment because of this significant leak. Now, a key thing to understand in the design to understand why this happened is that the way the sump pump was designed, the control logic was set up that the pump would automatically start as soon as the level reached the high level alarm point, and then it would turn off when it reached the low level alarm point. So by that design meant that every time the pump turned on as it was supposed to, it would generate a high alarm, which the operator didn't need to do anything for. So they got used to ignoring it. So with that, let's try and understand what happened. So why did the operator not take the correct action? Well, they incorrectly diagnosed the problem as something in the neutralization area. And they did that partly because they exhibited attention tunneling. They lost their situation awareness. They lost their ability to, at a higher level, look at the different process areas and try and figure out what's really causing what here, because they just focused totally in the neutralization area. They probably exhibited confirmation bias. I can't imagine that you would be making changes in the neutralization area and not see changes that you think corroborate your theory as to what is going on. So these were some of the reasons why they took the wrong action. Now, why did they ignore the high and the high level alarms in the sump? Well, it was because the high level alarm was a nuisance alarm, and it conditioned the operator that they could ignore alarms from the sump. Now, the operator should have known that the high should not be ignored, but you can understand that they might make that mistake in an upset where they're focusing on another area. But that also meant that they were exhibiting an errant mental model. Their understanding of how the process worked and how one part of the process related to another was wrong, because they focused and thought the issue was in the neutralization area, and it wasn't. Now, why was that sump high level alarm in the system? That's a good question, because it was not a valid alarm. If an alarm rationalization had been performed, it would have determined that that alarm was not valid and should be removed, because there was no operator action required and it was not an abnormal situation. So the operator was kind of led down the path of a false impression or understanding of what was happening because of the nuisance alarm, because of a failure in rationalization. Now let's look at another example involving a batch process where there was a modification to piping before a batch run. Unfortunately, that modification was done incorrectly, so that the material that the operator was delivering as part of the process went to the wrong tank. So during the production run, at some point a couple of days in, the operator got a high-level alarm on that tank. Well, it was the wrong tank, according to them, so they didn't respond to it or investigate it. A day later, they got another alarm. This one, a high alarm from that same wrong tank. They again ignored it, thinking that it was wrong, that there was something wrong with it. So they ignored those alarms until eventually they overflowed the tank and ended up spilling 1,000 gallons of materials into the dike. So when they investigated, or let's look at what they did wrong. So they, again, incorrectly diagnosed what the problem was. They considered the second tank to be out of service. So any alarms coming from that tank can't be credible, must be irrelevant. And that's what they thought. And they stuck to that thinking even as a second alarm occurred. So their mental model, again, of how the system was working at that time with the incorrect piping modification was wrong. And it caused them to incorrectly respond or to ignore those alarms. So they may have exhibited some confirmation bias, but certainly I would say they exhibited also some overconfidence. Why would they not have investigated the high-level alarm? Or certainly once you get the high, you would think you should at that point investigate, thinking that maybe your understanding of what's happening is not correct for some reason. Maybe your mental model is wrong somehow. They should have investigated that. This is actually a pretty common scenario, the idea of actions taking place on the wrong equipment. It's a very common error that's made, and it can be made for expert operators or done by expert operators. So that's one thing that can potentially be addressed in design to prevent that from occurring. Another scenario was a DCS migration. In this case, they did a rationalization as part of the migration. And for a tank that had both a high and a high alarm originally, the rationalization got rid of the high alarm and just kept the high alarm. So then the very first time that they started up the plant and ran the process after the migration, they had a toxic chemical release that shut down the highway. And that was because the operating procedure that the operators followed was to fill the tanks past the high-level alarm and wait till the high alarm occurs, and then they would shut down the incoming flow. So that was their operating procedure. That was not taken into account during the rationalization, which was done offline without help or support from the operators. So let's think about what happened there. Why did the operator not take the correct action here? Well, they had a high-level situation, but they dismissed the high alarm as being irrelevant because it was previously according to the way they operated the system. So their mental model then, after the reconfiguration, after the rationalization, was not correct. And by following the old procedure, that directly led to this incident. So was that a fault of the operator, or did it have to do with incorrect alarm rationalization? Or probably maybe the main thing would be a lack of training of what has changed after the rationalization and the alarm design was done. Now let's look at a different industry even, a rupture in a gas pipeline due to corrosion. So this rupture occurred, resulted in fires, significant damage, and one of the main problems was that the rupture or the leak was not detected right away. It actually took a good hour before the controller realized that they had a rupture. Now, this system did not have any automatic shutoff valves. They had designed it so that there were 3 sections within the alarm summary for alarms, a different section for alerts, and a different section for communication outages. And one of the problems that occurred was there were a lot of delta P, changes in pressure, alert notifications to the operator that they were not able to figure out what that meant, what that signified. And you can see here, you have a regular continuous drop in pressure, which should have been the indicator much earlier than it actually occurred that there was some kind of rupture and some kind of loss occurring. The operator was not able to make that assessment. So why did they take the wrong action? Why did they not take the correct action sooner? They actually, again, did not diagnose the problem correctly. Those delta P alarms, they were not able to figure out what that meant or understand the situation with just that information. And it wasn't until they got a call from another pipeline operator that told them that they had seen a fire and such that they understood what was happening. Now, part of the contributions to this was that there was no documentation or expected response to alerts. And in this case, there was truly an operator action required for these alerts, which is a little bit different from sometimes the way alerts are treated in a true process industry situation. Now, there was also a lack of situation awareness. So these alerts that occurred, there was no specific meaning behind them or time scale of response. The way they were presented as a notification, it was just an indication that the pressure had changed. It didn't even provide you information on whether it had gone up or down, and it didn't give you any reference into information as to what the actual absolute value of the pressure was. So making it harder for the operator to figure out what was happening. Now, one of the reasons why this situation occurred was from some management decisions by the company to reduce the frequency of nuisance alarms as measured by alarm system performance. They re-engineered their SCADA system to separate alarms from alerts. Alarms were then used just for safety related parameters, and alerts were used for operator defined controlling parameters, so not safety related parameters. And by separating it this way, they found that their alarm performance, just looking at alarms, was excellent and was within the expected performance thresholds of the ISA 18.2 standard. So they saw an average of 2 alarms per hour, with the target being 6 to 12 alarms per hour. But what this didn't take into account was they were now getting 95 alerts per hour. And in this case, the alert demanded a similar amount of attention as an alarm did. So from a cognitive processing point of view, the operator still needed to understand what was going on, give some thought to what was happening and what action they might need to take. So this was effectively like they were getting close to 100 alarms per hour, which is way more than what can reasonably be responded to. So because they had separated out the alerts from the alarms, it made the performance calculations look good, look better. But in reality, the operators were still overloaded with abnormal situations and abnormal notifications. So now let's take a look at a scenario where the human response to alarms is really, really important. and that is what we call safety alarms. These are alarms that are classified as critical to process safety for the protection of human life or the environment. As an example, the alarm and the beacon on this toxic gas detector for an analyzer shed, for example. This alarm and the hardware and the horn or the light and the operator taking the appropriate response is so important that if the operator were to go into this area when they shouldn't, they could end up not coming out if they are overcome by a toxic gas. So we want this system to be really, really, really reliable, meaning the hardware generation for the alarm, the enunciation of the beacon, and the operator to pay attention to what that says and what that tells them, and to do what they're supposed to, which would mean do not go in there without proper equipment if that beacon is active. And the only way we can get that kind of repeatable behavior from a human response point of view is if we do a lot of training and drilling on how you should respond. Similar to what happens to a fire drill, except most fire drills that I've ever seen don't get executed the way they should. You have people that stay back in a room here, or they question, do we really need to go out and respond to this? That's not a recipe for effective and reliable response. You want this scenario, the operator making the correct response, you want that to happen 99 out of 100 times for it to be done correctly, or even more frequently than that. And you're not going to get there if you do a fire drill where you may or may not respond, or you may or may not ignore the need to go outside. So let's look at some incidents where this came into play, the human response to a toxic gas detection. So here's an example from Laporte, Texas, where 24,000 pounds of methyl mercaptan, very toxic substance, were released inside a building, inside a manufacturing building. 3 operators and the shift supervisor were killed when they went into that building to investigate without respirators. And what they found was there was a toxic gas detection system in place and alarms in place, but they had been ignored and it didn't work very well, such that the operator normalized their response, or normalized the presence of toxic gas by actually using their nose to detect whether toxic gas was present or not. So that's positively not the response that we want from a human in that situation. Now, how did that happen? It got there because of the systems that were in place and the management structure that allowed it to happen are partly what led to that situation. Now, the last incident that we're going to look at is one related to the Aghorn operating water flood station, where there was a pump that failed, generating a high oil level alarm. And the stuff that that pump was pumping, produced water, actually contained H2S. So with that failure, H2S started to collect in the pump house. Well, that oil level alarm generated a call out to an employee to come to site and investigate. They went into the pump house and unfortunately never came out. They were overcome by the H2S gas. Now, that beacon should have been on in that situation and it should to indicate to the operator that don't go in there because it's a dangerous situation, or only go in there if you have the right breathing apparatus with you. But we don't know for sure whether the beacon worked or not. And this is an active investigation, so we don't know too much about the conclusions of what led to it. But It's another example of where this safety alarms and the alarm enunciation and the operator taking the correct response really is important. And in this case, somebody died because that system didn't work the way it was supposed to. So let's summarize and look at some key takeaways from these incidents that we have reviewed. So we should be designing to prevent human error. We can project scenarios that are more likely to lead to human error, and we should try to design to prevent that. The wrong equipment scenario, as I mentioned, is a common one, and that's an area that you can design the HMI to make it easier to prevent that from happening. You can also put error checking within the HMI, for example, to prevent an operator from entering a 50 when they meant to enter a 5, and you can do that to help prevent errors. We also want to design the system to support development of correct mental models and to deliver situation awareness for the operator. Part of how we do that is by designing the human-machine interface, the process graphics, to show confirming and supporting information. So other alarms, other process information that allow the operator to draw conclusions about what's really happening, to give them more information for their mental models, to really understand what's going on, and to potentially then address the potential errors that occur from an expert operator differently than from a novice operator, and making sure we're understanding the type of error before we implement the remediation step. And we also want to come up with a new way to think about human error. From a management point of view, if we want to really get to the root cause, we can't be looking at these as an opportunity to put the blame on someone like the operator. From the operator's point of view, you need to be more self-aware. You need to realize that you are prone to cognitive biases. You are prone to lose situation awareness when you dive into something and think that you truly understand what's going on. And maybe you should have a different way about thinking about alarms and equipment that's not working. And you should assume that the alarm is valid until you prove it otherwise, rather than the opposite, that it's something that you can ignore because you believe the equipment is not working. If we take a different tact and assume that it's correct until proven otherwise, that would save us from a lot of these incidents. From an engineering point of view, we need to realize also that human error is part of life. It's going to happen, but we can design the system to minimize or prevent it, and we should do that whenever we can. So thank you very much for your attendance. Hopefully you found this to be a useful and interesting webinar. Certainly, if you have any questions that you want to get answered, please put them into the questions box. As we're wrapping up, I just want to put a plug in for a upcoming alarm management training class that we're doing through the UK. This is for our flagship training class, Alarm Management for Practitioners, day-and-a-half long course where you can take the Alarm Management Practitioner Certificate exam at the end of it. Now that class is being held the end of April. It's also being held the end of June out of the US. And here's the schedule for other upcoming courses that are being offered by Exida. And of course, many of our courses are available online on demand so that you can listen to them whenever you like. So on that note, again, I'll say thank you for attending. I hope you enjoyed this webinar. If you did and you want to learn more, you can get access to previously recorded webinars either from the Exida website or from our YouTube channel. If you go there, you'll see that there's actually collections of videos for different topical areas: functional safety, cybersecurity, and the one for alarm management actually has 31 different videos there. And if you have any questions or comments, please feel free to reach out to me at the email address shown here, tstauffer@exida.com. And on that note, I'll say thank you very much and have a good rest of the day.